Alright, this video is going to cover the rest of section 1.6 and 1.7. I got a little ahead of myself in the last video and I forgot to talk about subtracting two vectors. So we'll start off with that and then we'll talk about vector components. So when you add two vectors, you place them tip to tail. So if you have this vector A and vector B, we start drawing vector B at the tip of vector A, and we get this nice resultant vector C here in red. Let me switch to the pen. Okay, so if we want to subtract B, that's the same thing as saying A plus negative B, or what do they do? Here they're actually just rearranging this equation. So if we take this equation, we can say C equals A plus B. So we can subtract B from both sides, cancels out over here, and we get C minus B equals A. So if we look at our vectors a different way, let's say we're taking C minus B, or that would be like C plus negative B. That should be equal to A. So if we start off drawing C, same C that we had up here, and then draw B in the negative direction, so it's the same size, same angle, but it's pointing the opposite way. So C plus negative B. Then if we draw a line from where we started to where B ended, we get our resultant vector, and sure enough that gives us A. So we see that this A is equal to C minus B, or C plus negative B. Here's another example. Here we have A plus B equals C. This is our C here. In this example, we're taking A minus B. So we still have the same A, same angle, same direction. And our B is the same angle with respect to the horizontal. See here. And this angle would be the same thing. But notice in this one, instead of B then pointing up and to the left, it points down and to the right. So we get a different C. We'll call this C prime. It's a different length, not only a different length, but it's also a different direction. Alright, let's talk about now vector components. So any vector can be taken and split up into components that are perpendicular to each other, and this is going to become really useful when you start to add multiple vectors together that are at odd angles to each other. Okay, so basically if we took, let's say this vector was actually a board or something, and we took a spotlight and we shone it on this board, it would make a shadow along the base here that's represented by this X. So this X is what we call the vector projection onto the X-axis. Same deal with the Y. If we took a spotlight over here and shone it on this direction, it would make a shadow that's like this Y. So these two vectors, notice if we started off with X and Y, if we covered up and we did X plus Y, putting Y at the tip of the X, our resultant is this R. So basically this is just the opposite of adding two vectors together. When you're finding vector components, you're taking a vector that's already at an angle and finding the two vectors that are at right angles to each other that make it up. Okay, so this is illustrating another way that you could draw the X and Y components. So oftentimes the Y component, instead of being drawn over here, like we saw in the previous example, we actually draw the Y component aligned with the Y-axis. Now it's the same thing, it's pointing in the same direction, it's at the same angle, it's completely vertical, and it's the same size. So it doesn't really matter where we draw the Y component, we could draw it in the middle if we wanted, and it's still the same. But often it makes sense to draw these along the coordinate axes. Other times it makes sense to draw them tip to tail to make a right triangle. It just depends on the situation. We're going to skip that part. We're not really going to use the notation x hat and y hat. If you want to read about that in the book, that's good to know for future reference, but we're not going to, that notation isn't really used in AP, so we're going to skip that. Okay, so here's an example of finding the components of a vector. So let's say we have a displacement vector with a magnitude of 175 meters, and it points at an angle of 50 degrees relative to the x-axis. Find the x and y components. Okay, so our first step would be to draw this diagram. So this may not be given in a problem. So first you need to know which direction you are drawing your vector. 50 degrees relative to the x-axis. So if we've got our y-axis and our x-axis, then the angle is 50 degrees as compared with x. And then you can just draw this an arbitrary length that represents 175 meters. That looks like 1.75. 175 meters. Okay, and our angle is already labeled here. So in this diagram, this would be our theta, here, this 50-degree angle. So to find the sides, we go back to SOHCAHTOA. We have one angle and one side that's known, and this is a right triangle. So as long as you know one angle and one side, then you can find the other sides and the other angle for that matter. So to find y, we would use sine. Remember, sine equals opposite over hypotenuse. So the sine of 50 would be y divided by 175, y divided by r. So that gives us 134. To find x, we would use cosine. Cosine, remember, CAH. Cosine equals adjacent divided by hypotenuse. So cosine of 50 is x divided by r. So since we know theta and r, we can then solve for x. So that gives us 112 meters. So altogether, again, this is the x and y notation. Basically, this is saying altogether, r is equal to 112 meters in the x direction. So that would be this, plus 134 meters in the y direction. And if you wanted to verify that using the Pythagorean theorem, you could. Okay, so here's an example of adding multiple vectors together. We have a plus b here. And notice that neither a nor b is straight perpendicular or horizontal. So how do we add these together? Well, we could use the law of sines or the law of cosines, but it's generally easier to just find the components of these vectors, and then you have everything at right angles to each other and you can more easily add them up. So this is illustrating that if we take a, we can represent it with its components, ax and ay. Those are just the projections along the x-axis and the y-axis. Same with b. b is made up of bx and by. So once we have drawn ax and ay, bx and by, these represent instead of a and b. So we can kind of now ignore a and b because these two and these two are there instead. They're equivalent to, these two together are equivalent to what a was, and these two together are equivalent to b. So then if we just slide these over, if we slide this a over here, and we slide the b down so it's aligned with the y or the x-axis, then that takes us to this picture here. So we've just taken the a that was over here and slid it over, and we've taken the b that was here and slid it down. So now you can see we have one nice big right triangle. Since these are defined as being along the x and y axis, we know this is a 90-degree angle. So then if you have found ax and bx, you can simply add the numbers together since they're in the same direction. Same with ay and by. That makes the math a lot easier. So then you can come up with a total cx and cy for each side. So cx is just equal to ax plus bx. And cy is just ay plus by. Okay, so this is showing that side C here is equal to the vector A plus the vector B. You could also write this as C is equal to AX plus BX plus AY plus BY. And group these that are in the same X direction together and these two that are in the same Y direction together. And as long as these are in the same direction, then you can just add those numbers together. Alright, we'll do some more examples of that in class.